Okay, I'm gonna get started. So, homework number 7 on chapter 8 is due on the 29th. That's Wednesday. Homework number 8 on chapter 9 will be due on the 5th. That's next week, Wednesday. Next week, Monday, we will have review on the 3rd. And next week, Wednesday, we will have the exam on chapters 7, 8, 9. We will have a lab on Wednesday. We will not have a lab on the day we have the exam. I'm not going to do a lab and the exam on the same day. The exam will be similar to the previous exam, about 10 questions. Similar sort structure. You get one sheet of notes to use as a reference sheet for formulas. I don't know exactly how many because I'm adjusting it at the moment. So, linear momentum. So we were talking about linear momentum. Linear momentum. P is equal to mass times velocity. And it's a vector. Its direction is the same as the direction of the velocity. And impulse relates force to momentum. So impulse is the average force times time, which is the change in momentum. The net force is equal to the change in momentum over time. If the net force is 0, the momentum does not change. If you have a system of objects, if the net external force is 0, the total momentum of the system doesn't change. So for a system of objects, you have internal versus external forces. Move this up. Internal forces act between objects within the system. And because of Newton's third law, they're all action-reaction pairs. So if you add up all the internal forces, they all cancel out and add up to 0. Therefore, the net force acting on a system is the sum of the external forces acting on it. And that will relate to the change in momentum of the system. So if there are no external forces, momentum is conserved. Internal forces cannot change the momentum of a system. However, the momentum of components of the system can change. So we talked about collisions. We were talking about inelastic collisions. A collision is when two objects strike one another. The time of the collision is short enough that external forces can be disregarded. Inelastic collisions, momentum is conserved, but kinetic energy is not. And completely inelastic collisions, the objects stick together afterwards. So for a completely inelastic collision between two objects, you have mass 1, velocity 1, initial, plus mass 2, velocity 2, initial, equals mass 1 plus mass 2 times final velocity. So this is a completely inelastic collision. Before you have two vehicles with two velocities, and then merge into a single unit because they're coupled together. So if you solve for final velocity, you get this formula. mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, over mass 1 plus mass 2 is final velocity. Now here is a 2D version of this. So in 2 dimensions, you can still have inelastic collisions. Momentum is conserved in the x direction and in the y direction. So you can treat each axis independently. So here, we have a car with a mass of 950 kilograms and a speed of 16 meters per second. Approaches an intersection as shown in the sketch. A 1,300 kilogram minivan traveling at 21 meters per second, setting for the same intersection. They collide and stick together. Find the direction and speed of the wrecked vehicles just after the collision, assuming external forces can be ignored. So I'll give you a few minutes to work on this. So mass 1 is 950 kilograms. Mass 2 is 1,300 kilograms. Velocity 1 initial is 16 meters per second in the positive x direction. Velocity 2 initial is 21 meters per second in the positive y direction. We want to find the velocity, the final velocity, and we want to find direction and speed. So we'll need to find its magnitude. So initial momentum equals final momentum. So mass 1, velocity 1 plus mass 2, velocity 2 equals mass 1 plus mass 2, velocity final. So velocity final is mass 1, velocity 1 plus mass 2, velocity 2 over mass 1 plus mass 2. So 950 kilograms plus 16 meters per second in the x direction plus 1300 kilograms times 21 meters per second in the y direction over 950 kilograms plus 1300 kilograms, which simplifies down to 6.76 kilogram meters per second in the x direction. Oh, wait, no, that's a typo. Oops. This is just meters per second. Oops, misclick. Sorry, that simplifies down to 6.76 meters per second in the x direction and 12.1 meters per second in the y direction. So the final velocity, if we want to find the magnitude, we can take the square root of the x squared plus the y squared, and we get 14 meters per second. And the angle is the inverse tangent of 21 meters per second over 6.67 meters per second. And so the angle is 61 degrees. Again, it's just meters per second. Thinking about momentum too much. Any questions about that? Okay. So that's how you deal with two dimensions. You can do x and y independently. You can combine them into one big equation with the x hat and the y hat. Both work. So two objects travel in opposite directions along a straight line. They have momenta of equal magnitude and they stick together when they collide. What is the final speed of the two objects? And what percentage of the initial kinetic energy is converted to other forms as a result of the collision? So I'll give you a couple of minutes to think about this. Both objects have the same momentum of equal magnitude, but are traveling in opposite directions. So momentum initial equals momentum final. So that's momentum 1 initial plus momentum 2 initial. But these have momenta of equal magnitude in opposite directions. So momentum 1 initial equals minus momentum 2 initial. So minus momentum 2 initial plus momentum 2 initial equals momentum final. Our final momentum, our initial momentum, and our final momentum equals 0. They have equal momentum in opposite direction. The total equals 0, which means our final velocity is 0. Because they come together and stick, they're going to come to a stop. Because our final velocity is just the final momentum divided by the total mass, because they stuck together. Our final velocity is 0. Therefore, our final kinetic energy is 0. So 100% of the kinetic energy was converted into other forms. Yeah, that's that. So now let's talk about the other kind of collision, elastic collision. And I guess I can give a decent demonstration of some elastic collisions, mostly elastic collisions. Here, these collisions are mostly elastic. They're not perfect, but you can see it sort of transferring energy back and forth. They're bouncy collisions. So collisions with lots of bounce are allowed. There are ways to classify partially elastic collisions, but we're not going to deal with that in this class. So in elastic collisions, both kinetic energy and momentum are conserved. In a one-dimensional elastic collision, you have a mass. So here is an example where you have some mass traveling along, it hits something at rest, and then afterwards they're both moving. And the total momentum is conserved and the total kinetic energy is conserved. And knowing that, and knowing the initial conditions, it's possible to figure out the final velocities from the initial velocities. So these are the equations. If you have two objects colliding in one dimension, this is conservation of momentum, mass 1 times velocity 1 initial plus mass 2 times velocity 2 initial equals mass 1 times velocity 1 final plus mass 2 times velocity 2 final. And then here we have conservation of kinetic energy, mass 1 times velocity 1 initial, 1/2 mass 1 times velocity 1 initial squared, plus 1/2 mass 2 times velocity 2 initial squared equals 1/2 mass 1 times velocity 1 final squared plus 1/2 mass 2 times velocity 2 final squared. This can be simplified down to conservation of momentum, and then V1 initial minus V2 initial will equal minus V1 final minus V2 final. I'm not going to go through the math to simplify to that, but if you have one object at rest, this is a simpler case. We get the solution. So this is V1 final equals. So this is one object at rest, where V1 initial equals V0, V2 initial equals 0. So you have M1 minus M2 over M1 plus M2 times V1 initial, V2 final equals 2M1. Actually, let me write this a little smaller because I'm going to extend it. So all the problems you're going to have to deal with, you will be able to solve with these equations. because all of them are going to be one object moving, the other one at rest. So you could use conservation of momentum and conservation of kinetic energy and the two unknowns, the final speeds. You could solve that and get these equations. Now, it turns out you can solve it if V2 initial is not 0 as well. It's just harder. So they only went through the solution in this case in your book. But I will give you the general solution. So the general solution for both objects initially moving is this. Initial 2 minus 1 or 1 plus 2 v2. Yeah. That's, you just actually do a switch where you switch all ones to twos, and that gives you the second set of terms. So that's the general solution. But again, all the problems we will have, we'll use this simpler version where only one object is moving initially. So here at an amusement park, a 98.5 kilogram bumper car moving with a speed of 1.18 meters per second. Just check. Bounces elastically off of a second 122 kilogram bumper car at rest. Find the velocities of the two cars. So I'll give you a little while to work on it. Sure. So this is fairly straightforward. As long as I make things work. So mass 1 is 98.5 kilograms. Mass 2 is 122 kilograms. V1 initial, which is V naught, is 1.18 meters per second. V2 initial is 0 meters per second. V1 final is what we're looking for, and V2 final is the other thing we're looking for. So V1 final will equal mass 1 minus mass 2 over mass 1 plus mass 2. And that V2 final will be 2 times mass 1 over mass 1 plus mass 2. So V1 final is going to be 98.5 kilograms minus 122 kilograms over 98.5 kilograms plus 122 kilograms times 1.18 meters per second, which comes out to negative 0.126 meters per second. Mass velocity 2 final is 2 times 98.5 kilograms divided by 98.5 kilograms over 122 meters per second times 120, 98.5 plus 122 kilograms, all times 1.18 meters per second, which comes to 1.05 meters per second. So this will bounce backwards, this will bounce forwards. Most of the kinetic energy is moving forwards. That's the final velocities of the two cars. Here we have a hoverfly happily maintaining a fixed position about 3 meters above the ground when an air elephant charges out of the bush and collides with it. The fly bounces elastically off the forehead of the elephant. If the initial speed of the elephant is V0, is the final speed V of the fly after the collision equal to V0, 2 V0, or 3 V0? So what do you think is going to be the closest to the final velocity of the fly? Remember, the mass of an elephant is much, much, much bigger than the mass of a fly. So this is fairly straightforward. Our final velocity is going to be just this part of the formula, because our V0 is the mass of the elephant. That's our V1 initial. That's the velocity of the elephant. And we want to find the final velocity of the fly. So V is going to be 2 times the mass of the elephant over the mass of the elephant plus the mass of the fly, all times V0. But the mass of the elephant is much bigger than the mass of the fly. So that means the mass of the elephant plus the mass of the fly is approximately the mass of the elephant. So V equals 2V mass of the elephant over mass of the elephant times V0, or just 2V0. So it'll bounce off the elephant with twice the initial velocity. Basically, the fly is so light that the elephant just dumps energy into it. So 2V0. We were talking about elastic collisions. So here's another problem. The 1 kilogram block shown slides to the right on a frictionless surface and undergoes an elastic collision with a 2 kilogram block that is initially at rest. What is the direction of travel of the 1 kilogram block after the collision? And which block has the greater speed after the collision? So I'll give you guys a few minutes to do that. So let's start with finding the direction of travel of the 1 kilogram block after the collision. So to do that, we need to figure out its final velocity. So the final velocity of the 1 kilogram block is going to be mass 1 minus mass 2 over mass 1 plus mass 2 times our V naught. Our V naught in this case is just some V naught, V. And mass 1 is 1, mass 2 is 2. So that's 1 kilogram minus 2 kilograms over 1 kilogram plus 2 kilograms times V. So that's minus 1/3 times V. So our final velocity is negative. So the direction of travel of the 1 kilogram block will be to the left. It bounces off and goes backwards. Which block has the greater speed? Just in general, if you have a lighter thing moving, hitting a heavier thing, it's going to bounce backwards. Because you have mass 1 minus mass 2. So it moves to the left. What block has the greater speed after the collision? Well, we know the speed of V1 is 1/3 of V, our initial velocity. We want to find the speed of V2. V2 final is going to be 2 times mass 1 over mass 1 plus mass 2 times V naught. So 2 times 1 kilogram over 1 kilogram plus 2 kilograms times V naught. Oh, it should be V. So V2 final will be 2/3 V, which is a larger speed than 1/3 V. So block 2 has the greater speed. Let me fix those real quick. No. Well, we can also do two-dimensional collisions. Now, we can only solve two-dimensional collisions if some of the final information is known, such as the final velocity of one of the objects. And in general, you can use kinetic energy and you can also use momentum. So, this is sort of, here's an example. before, you know the initial velocity of this at rest. Afterwards, you know the velocity of one of the objects. You can figure out the velocity of the other object. And you can do this with just momentum, it turns out. You don't actually need kinetic energy. So it can make it easier. So here's a problem. Two astronauts on opposite sides of a spaceship are comparing lunches. One has an apple, the other an orange. They decide to trade. Astronaut 1 tosses the 0.13 kilogram apple towards astronaut 2 with a speed of 1.11 meters per second. And the 1.60 kilogram orange is tossed from astronaut 2 to astronaut 1 with a speed of 1.21 meters per second. Unfortunately, the fruits collide, sending the orange off with a speed of 1.16 meters per second at an angle of 42 degrees with respect to the original direction of motion. Find the final speed and direction of the apple, assuming an elastic collision. Give the apple's direction relative to its original direction of motion. So you can do this just with conservation of momentum, or you can do it with conservation of kinetic energy and conservation of momentum. Both ways work. I think the book does conservation of kinetic energy and momentum. My first instinct is to do this one with just conservation of momentum. But the general idea is you break it up into X and Y directions and work out things from there. And it would be possible to, in general, work this out with I think you could work it out with even less information than is given in this problem. But you could have 3 unknowns and get away with that. But it would be a pain. Yeah. Yeah, you probably work it out if you just had one of the final speeds, but you didn't necessarily have the angles. I think you can work it out. I'm not 100% sure there. Yeah, you could. Definitely. So let's do this. Mass 1 is 0.13 kilograms. Mass 2 is 0.16 kilograms. V1 initial is 1.1 meters per second in the x direction. V2 initial is minus 1.21 meters per second in the x direction. V2 final is 1.16 meters per second at 42 degrees. V2 final is something at something. Okay, I'm doing this like the book did. That's right. I don't remember what I put in here. It's possible to just do this with momentum, but I'll do it like the book did. Kinetic energy initial equals kinetic energy final. So 1/2 mass 1, velocity 1 initial squared plus 1/2 mass 2, velocity 2 initial squared equals 1/2 mass 1, velocity 1 final squared plus 1/2 mass 2, velocity 2 final squared. So 1/2 1.3 times 1.1 meters per second squared plus 1/2 0.16 times 1.21 meters per second squared equals 1/2 0.13 kilograms times V1 final squared plus 1/2 0.16 kilograms times 1.16 meters per second squared. So you get 0.197 joules as your initial kinetic energy. That equals 1/2 0.13 kilograms times V1 final squared plus 0.108 joules. So V1 final equals the square root of 2 times 0.197 joules minus 0.108 joules over 0.13 kilograms, or 1.17 meters per second. So that's the first part. We've got the velocity of the apple. Now we need to figure out its direction. We've got its speed, now we need to figure out its direction. So I'm going to go to another slide. We know its speed, we're looking for the direction. Momentum initial equals momentum final. Momentum initial y equals momentum final y. So initial momentum in the y direction is 0. So that's going to be mass 1, velocity 1 final times sine angle theta minus mass 2, velocity 2 final times sine 42. So mass 1, velocity 1 final times sine theta equals mass 2, velocity 2 final times sine 42. So sine theta equals mass 2, velocity 2 final times sine 42 over mass 1, velocity 1 final. Sine theta equals 0.16 kilograms times 1.16 meters per second. That's sine of 42 degrees over 0.13 kilograms times 1.17 meters per second. So sine of theta equals 0.817. So theta is the inverse sine of 0.817, which is 58.4 degrees. So V1 final is 1.17 meters per second and an angle of 54.8 degrees. And it's possible to get the initial velocity. Well, it's possible to just use the momentum equations. So this momentum equation to get the momentum velocity in the y direction, and then the other momentum equation for x to get the velocity in the x direction, and then combine them to get the total magnitude and direction. It's just two different ways to do the same thing. So let's talk about center of mass. So that was elastic collisions. Any questions about elastic collisions? All right, so let's talk about the center of mass. We did a whole lab about the center of mass. That was the balance one, had center of mass in it. The center of mass of a system is the point where the system can be balanced in a uniform gravitational field. So that point where you can balance it. So the center of mass is actually the point that's sort of the average location of all the mass. It's sort of the natural middle of the mass. And it turns out the way you can get center of mass, so for two objects, the center of mass is just the mass of the first object times its position plus the mass of the second object times its position divided by the mass of the two objects added together. Center of mass, so center of mass is just a weighted average. So it is the sum of mass I, xi, over the sum of mass I. So it's the average of position weighted by mass. So you do mass times position for every object and divide by the total mass. And you can in fact do center of mass for something that is like a substance. Then instead of it being a sum, you do an integral. So the center of mass can also be integral of density times position dx over the integral of density dx. But not going to do that at all. Now the center of mass is closer to the more massive object if you have two objects. If you have multiple objects, or if you have a funky shape, the center of mass doesn't need to be within an object. For an object that is convex, like a book or a bowling ball, it will be. But you can have something with a hole in it, like this, or you can have something that's like L-shaped. The center of mass can end up outside the object. But here, you know, like this donut, the center of mass is in the air in between. You have a question? Okay. Now, that center of mass can move. And it turns out we can just do the same thing we did with position for velocity. The velocity of the center of mass is just the sum of the individual masses times the individual velocities over the sum of the individual masses. And the same thing for acceleration. Oh, that should be a vote. The acceleration of the center of mass is the sum of the individual masses times the individual accelerations over the sum of the masses. And the same formula applies to y as it does to x, of course. So the center of mass can move. You can find the center of mass given some things. If you have some objects that have continuity, but you know their center of mass is, and you want to figure out where the center of mass of like a group of objects is, you can use the position of the centers of masses. So we have a problem that does that. The total mass times the acceleration. Okay, let's get this. The total mass times the acceleration is equal to the net external force on a system. So the center of the mass accelerates as though it were a point particle of mass, total mass, acted on by force, net external force. So if you like launch a firework and it explodes, the path of the center of mass continues on a parabola as the individual particles spread out from the explosion. So here's an example problem. Suppose the masses below are separated by 0.8 meters, and mass 1 is 3.25 kilograms, and mass 2 is 0.166 kilograms. What is the distance from mass 1 to the center of mass of the system? So mass 1 is 0.325 kilograms, mass 2 is 0.166 kilograms, x1 is 0 meters, x2 is 0.8 meters. And we want to find the position of the center of mass. Well, the position of the center of mass is going to be the sum of the masses of the individual objects times the positions of the individual objects over the sum of the individual masses. So that's going to be mass 1 times x1 plus mass 2 times x2 over mass 1 plus mass 2. So that's 0.325 kilograms times 0 meters plus 0.166 kilograms times 0.8 meters divided by 0.325 kilograms plus 1.66 kilograms. So x center of mass will be 0.27 meters. Here's a problem of center of mass with some actual objects. So a person's arm is held held with the upper arm vertical, the lower arm and hand horizontal, like shown. So this is going to be a two-dimensional center of mass problem. So for this, X center of mass is this formula. And you can do the same thing for Y. So Y center of mass is the sum of all mass individual times Y individual over the sum of all mass individual. So the upper arm has a mass of 2.5 kilograms and the center of mass 0.18 meters above the elbow. So for this, you could treat the upper arm like a single object at its center of mass. Same for the lower arm and the hand. The lower arm has a mass of 1.6 kilograms and a center of mass 1.2 meters to the right of the elbow. The hand has a mass of 0.64 kilograms and a center of mass 0.4 meters to the right of the elbow. So the question is, find the center of mass of this arm. In the book, there's another part where they add a baseball on the hand, and you need to find the center of mass with the baseball, but we're not going to do that. So I'll give you a few minutes to work on this. So let's start with what we know. Mass of the upper arm is 2.5 kilograms, and it's at x equals 0 and y equals 1.8 meters. Mass of the lower arm is 1.6 kilograms, and it's at x equals 1.2 meters and y equals 0 meters. Mass of the hand is 0.64 kilograms, and it's at x equals 0.4 meters and y equals 0 meters. And we're looking for x center of mass and y center of mass. So x center of mass is going to be the sum of all masses, mass times x, mass I times xi, sum of all those, divided by the sum of all the masses. So that's mass of the upper arm times x of the upper arm plus mass of the lower arm times x of the lower arm plus mass of the hand times x of the hand divided by mass of the upper arm plus mass of the lower arm plus mass of the hand. So that's 2.5 kilograms times 0 meters plus 1.6 kilograms times 1.2 meters plus 0.64 kilograms times 0.4 meters over 2.5 kilograms plus 1.6 kilograms plus 0.64 kilograms. So that's 0.488 kilogram meters over 4.74 kilograms, which is 0.095 meters. Y center of mass is mass of the upper arm times y of the upper arm plus mass of the lower arm times y of the lower arm plus mass of the hand times y of the hand, all over mass of the upper arm plus mass of the lower arm plus mass of the hand. So that's 2.5 kilograms times 0.18 meters plus 16 kilograms times 0 meters plus 0.64 kilograms times 0 meters over 2.5 kilograms times 1.6 kilograms times 0.64 kilograms. So that's 0.45 kilogram meters over 4.74 kilograms, which is also 0.095 meters, rounded to two significant figures. This is ever so slightly higher than this, but it rounds to the same value of the two significant figures. Any questions? So you can just do x and y separately for center of mass. And I think we'll cover this one next time, and I think we're good to go for today. So I'll see you guys on Wednesday when we'll finish off chapter 9 and start chapter 10. And then next week we'll have the review and exam for chapters 7, 8, and 9. So let me stop sharing. Okay, I'm going to end the meeting.